welcome back to the second lecture of week 5, which is lecture 22 of Financial Mathematics for Actuaries. Today we are going to handle a delicate topic of continuous annuities. What if money flows like water? How will you discuss annuities in that context, right? So let us differentiate with what we have already studied and how will this be different. So far we studied discrete annuities where we studied perpetuities also, but the logic remains same. When we studied discrete annuities, the payments are happening in chunks. They are either monthly, yearly, and therefore it is similar to stacking brick one by one. You are actually building something where you are stacking the bricks, and therefore the tool that we required was essentially the geometric sum. So summation was good enough for us, and then we didn't really use those sums, we used those formulas for geometric sums to evaluate these annuities. Annuities immediate, annuities due, and perpetuities over discrete time. Now let us say the ball game has changed. Now payments are coming continuously and there is a continuous flow. For example, your utility bills are charged on your consumption. The toll roads where they collect the toll, they are getting the money continuously. So all these things are happening continuously. So it is similar to water which is filling a pool, correct? So whenever there is a continuous stream, we cannot work with summations, we need to work with integrations, right? Okay. One common point between summation and integration is this, we have already shown this, that as the summation are happening more and more frequently, that is the time horizon shrinks, summation actually becomes integration. This is the bridge that we will explore today. Okay. So in order to explore that bridge, let us first discuss today's roadmap. So today's roadmap starts with first understanding this transition from discrete to continuous. So we will visualize this transition from discrete to continuous. Once we have visualized this, we will appeal to our older knowledge of week 3 and week 2, and we will derive the formula using calculus principle, and it deals with e raised to delta t. Okay. Once we understood this, we have visualized and we have derived the formula, then it is natural step to relate this with whatever knowledge we have, that is discrete annuities. And then naturally once we have understood the concepts, it is worth trying them on some use cases which are toll roads and continuous savings. As usual, I have given the reference mapping, Brouwerman section 2.2, Chan and Say section 2.5. You should read these texts in order to have elaborate understanding on this topic. Okay. So let us begin with visualizing the transition. So here is the graph where we are collecting the payments, and as year passes by we are decaying in value, right? So that's the whole idea that we are having. So now if you look at this, when we are in discrete time zones, what we are doing is whatever is happening with these green boxes. What if you try to shrink the lengths of these green boxes? There will be more green boxes and you will have more and more approximations. So for example, if I shrink the green box length to this level, then I will have this kind of approximation, right? So I am actually having more closer and closer, I am becoming more closer and closer to the actual blue line that is there, right? So that's what is happening when payments are coming on a continuous basis, and I cannot actually handle those payments using these discrete time points, because we have already seen when we are compounding and when we discuss the force of interest, the money becomes larger and larger. So when ultimately what happens, when these boxes shrink to a very infinitesimal length, we have something like this. and that is actually area under this curve. And how will I calculate? For that I will consider a small interval which is dt, and I will actually consider a rectangle around this, and because this dt has very small length, the length of this interval will contribute significantly. What was this? This was our interest rates, right? And those were, if you remember those things, then those formulas were 1 plus I, right? And your V into 1 plus I was equal to 1. So, your V was 1 upon 1 plus I. This was the interest rate. And then as we increase in time, we are getting V raised to n, which is 1 plus I raised to 1 upon 1 plus I raised to n. Remember our bridge equation when we related this 1 plus I to e raised to delta, and this delta was your force of interest, right? That is where we shrinked all those boxes and we calculated I infinity, if you remember. And that I infinity I will appeal to now, and that will give me e raised to delta, and same thing I will use now in order to calculate this particular area under the curve. Okay. So, we will sum over these infinite slices and this summation will become an integration. So, let us see how this knowledge translates into calculation of annuities for continuous compounding. So, first thing that we have noticed is our discount factor for time t is v raised to t, which is equal to e raised to minus delta t. Okay. Now, we need to sum over the payments from 0 to n, right? For in each payment where we are considering that infinitesimal length of time period dt, that is my payment, and it is discounted by the factor of e raised to minus delta t. And now what I want to do is I want to sum over all these things, right? So, I will integrate over all of them, and that is what will give me this. Okay, that is equal to a bar. So, notice the difference, there is a bar over here, angle n. So, this denotes the compound continuous payments, continuous annuities. Okay, I will integrate this out, then integration gives me this to be equal to this e raised to minus delta n will be there, and then it gives me finally e raised a n to be equal to 1 minus v raised to n upon delta. So, where is this v coming from now? Okay, so this one is this particular thing is 1 minus e raised to minus delta n upon delta. You relate this with e raised to minus delta, and that is what is our v. If you go back to this slide, 1 plus I is e raised to delta. So, 1 v is equal to 1 upon 1 plus I, which is e raised to minus delta, and therefore, I will get this e raised to minus delta as v, and therefore, I got this formula, correct. So, we got this formula, and that is what we are dealing with continuous annuities if your money flows like water. Okay. So, now you can notice that the numerator has not changed, it is 1 minus v raised to n, whatever is your discounting logic. Only with that discounting logic, whether you will put I or delta, that changes. However, our denominator slice machine, the denominators change based on the payment timings. So, first, if it is immediate, you are dividing by I. If it is due, which is starting at the beginning of the period, you are dividing by d, and now it has come to continuous, you are dividing by delta. So, this actually tells you the relation between the immediate and continuous. Okay. However, if you look at this delta and if you look at I, if delta and I are close to each other, which is usually the case when the interest rate is small, then you do not have to distinguish between them because delta by I will be 1. Okay. But if they are different, then this correction actually applies for discrete annuities to continuous annuities. So, continuous annuities, you have a denominator of delta. So, what you do? You multiply and divide by I. So, you get annuity which is immediate into I by delta, that is all. So, that means if I want a continuous annuity A bar angle n, it is equal to A angle n into I by delta. So, that is the correction. Now, we have understood that this interest rate and delta, we have very specific relation, right. So, discounting interest rate and delta, we have shown that the delta was a balance point, right. So, what was different there? There we have already seen the intuition that this compounding that is required should be smaller in order to achieve the same I, discrete compounding, right. So, that means the money, if you are flowing as a continuous flow, the interest that you will earn will be more. Okay. So, that is the next intuition that we are dealing with. So, if you are saying the money is coming on a continuous flow, your average will happen at 0.5, and that is where you will start earning interest on an average. Okay. Whereas, if you are earning on a discrete time point which is 1, then it is you are actually receiving the money late. So, the interest will come later. Okay. So, continuous money will arrive earlier than discrete time points, and earlier you receive the money, the sooner it starts getting interest. So, it is worth more. Okay. So, that is the important takeaway here. Now, let us look at the problem that we handled in the last lecture, which is if I do not want to stop this flow, I want to continue forever, that is called perpetuities, and now we are dealing with in continuous perpetuities. Okay. So, the flow never stops and tends to infinity. What will happen? So, again the same logic applies. You have v raised to n in the denominator, and that v raised to n again as n tending to infinity will naturally tend to 0, because now it is e raised to minus delta. Okay. E raised to minus delta raised to n. So, it will again go to 0 as n tends to infinity, because e raised to minus x tends to 0 as x tends to infinity. Okay. So, because of that again the same thing will happen, and therefore, your a bar infinity will be nothing but 1 by delta, correct. So, the intuition behind this is very clear. If I want to get $1 per year on a continuous basis, I must need a fund of 1 by delta. Now, you compare this to 1 by I for discrete, which is obvious, right. So, it is 1 by I for discrete and 1 by delta for continuous. Okay. So, this brings us to a theoretical understanding of continuous annuities and continuous perpetuities. Let us apply this to a real world problem, which is the toll booth problem or a toll road problem. Assume that a toll road generates $1 million a year continuously for 20 years. Interest rate is 6%. You are asked to find the present value of that income that the toll booth is generating. So, here notice that I is given to you, and therefore, you will need a bridge equation. So, here what you will do, you have to find this delta, right, and as I already mentioned, 1 plus I is e raised to delta. So, our log is our friend. So, I will appeal to that log friend, and ln of 1 plus I will be equal to delta, right. So, what is 1 plus I here? It is 1.06. So, we will put that, and that is our step 1, which is find delta. Delta is equal to ln of 1.06. So, it comes out to be 5.827%. Okay. Once I have this formula, what is a question? delta is known to me, it's 1 million toll road is generating. So, the 1 million thing is going to be the PMT of our formulation, right, and this is going to be for 20 years. So, I need to calculate that 1 minus V raised to n upon I, but here it is a continuous thing. So, it is delta, continuous annuity, right. So, this was our A bar n, right, A bar n, that's the idea. So, that is what I need to compute. Do I know V? Yes, I know V because it is 1.06 raised to minus n, that's going to be this V raised to n. Okay, 1 upon 1.06 is my V. So, 1.06 raised to minus n, this n is actually 20, okay, and then 1 minus this upon, what is my delta? Do I know? Yes, I do know, it is 0.05827. Just do this calculation and then you get the answer to be equal to 1 crore 18 lakh 10,456. Okay, so that is going to be the value of that toll road. So what we have done is we have actually theoretically calculated this value. So now this B, when you come to calculator, this BA2 plus do not have this continuous button. So one way is you use your conventional method, you calculate delta by using ln of 1 plus I, store it in your memory and do the regular algebra, which is quite convenient. However, if you want a trick, you can use this infinite frequency trick that I am mentioning. It is very risky. Sometimes it may give wrong answers, but most of the times it gives correct answers. The idea here is the payments per year that you are trying to set, you set it to a huge number. Okay, it can be 5,000, it can be 10,000 and so on and so forth, right. Now, once you have set these payments for year, you change your number of periods, which gives capital N appropriately. So, in this case it was 20 years, every year you are supposed to have 5,000 payments. So, capital N becomes 1 lakh payments, okay, and then feed in this interest rate PMT, which is basically the amount yearly amount divided by the number of payments that you are doing. In this case I have chosen 5,000, so it is becoming 200, and then you say compute p value. This gives me the answer as 1 crore 16 lakh 46,727. So, this answer is significantly different from the answer that I received, correct. It is 1 crore 18 lakhs 10,456. This is 1 crore 16 lakh 46,727. So, which is close to exact answer, just because the hugeness or the numbers are being bigger, the rounding off error crept in to our calculation. So, this trick is very risky. Sometimes for lower level of payments this may work, in this case it is not working properly, okay. So, this is a demonstration that you should not always rely on calculators, you can also derive this easily using theoretical formula, which is option A. Okay. Now, it is your time to try this continuous saving problem. Problem is, you are depositing money continuously at the rate of 2,400 per year, okay. Your account earns force of interest delta equal to 4%. You are asked to find the value after 10 years. I have skipped the calculations for future value. I have done all the calculations for present value, but you already know how to calculate future value. If you know present value, you you go ahead to those many time periods ahead, multiply by 1 plus I raised to n, okay, if you are moving by n time periods. So in this case, that 1 plus I is actually e raised to delta. So you already know the formula for future value, which is S bar angle n is e raised to delta n minus 1 upon delta. Now apply this formula and calculate the value after 10 years. Pause the video. Welcome back. So I have applied that formula. 2400 is the payment, 4% is the force of interest. So e raised to 0.04 into the number of time periods, that is 10 minus 1 upon 0.04. Now it's simple algebra. You simply solve it. You will get the answer to be equal to $29,509.48 is going to be the future value. Wonderful. So we have covered a lot actually. Today what we have done is we have introduced a concept when the payments flow like water. What is essential consequence of that for us? If we are dealing with the annuities formula, you replace it with delta instead of I. Can I compare this with discrete compounding? Yes, I can do it with discrete annuities, and in that case, what is the connection? Multiplier is I by delta. If I have discrete annuity, multiply it by I by delta, I get continuous annuity. Correct? Calculator, I have shown you how to use theoretical formula and get the answer, or you can use large p by y approximation, but it is really an approximation, so do not rely on it. Okay. Now we will handle in the next lecture a most difficult problem where we are deferring the benefit of annuity by a certain period. We are starting late, okay, and how we will handle that situation, whether it is beneficial or not, we will see in the next class. So I am excited to see you in the next class. Thank you.